Hello, dear students. So, yesterday we have ended our discussion on the electrostatic potential energy of a system of your point charges. So, we will continue our lecture like after this. So, the next topic which we will see here is our that is just a second. Electrostatic potential energy of a system of 2 point charges we have covered in the previous lecture. So we will continue our discussion after that only. So there is an example 14. Let's see that what it says. In a hydrogen atom, the electron and proton are bound at a distance of about 0.53 angstrom. Estimate the potential energy of the system in electron volt. Okay. Taking the zero of the potential energy at infinite separation of the electron from proton. What is the minimum work required to free the electron given that its kinetic energy in the orbit is half the magnitude of potential energy obtained in first part. So this is the second part. Okay. What are the answer to first and second above if the zero of potential energy taken at 1.06 angstrom separation? So we have to just find out these three parts and let's see that how the calculation will be done here. Okay. So charge on an electron is what? You already know that charge on an electron is 1.67 into 10 to the power minus 19 coulomb. And charge on proton is also equal to 1.6 into 10 power minus 19 coulomb, but it will be in positive value, and in electronic charge it will be negative value. So R is given already here 0.53 angstrom. Okay. Now potential energy of the system is what? Potential energy at infinity minus potential energy at a distance of 0.53 angstrom. Okay. And because we already know that potential energy of any system is equal to what? Like infinity, we will take infinity as your reference point and minus the potential energy at the system in the required distance. So here 0 is the potential energy at infinity minus 1 by 4 pi epsilon naught 2e qp upon r. So this formula we already covered in the previous discussion. So that is why we have used this formula. Now substitute the value of your 1 by 4 pi epsilon naught, that is 9 into 10 power 9, and the charge values we had put here minus 1.6 into 10 power minus 19 and plus 1.6 into 10 power minus 19. Then the denominator you write 0.53 into 10 power minus 10 because your angstrom is what? 10 to the power minus 10 meter. Okay. That is why we have multiplied with 10 power minus 10 in the denominator part. And 1 electron volt is equal to 1.6 into 10 power minus 19 joule. This relation you must remember. That 1 electron volt energy is equal to 1.6 into 10 to the power minus 19 joule. Okay. So that is also used here. Because if you find out the value here, that will give in the answer joule only. It is coming out equal to minus 43.47 into 10 power minus 19 joules. Okay. Now divided by 1.6 into 10 power minus 19, you will get minus 27.16 electron volt. So this is your final answer for this question for first part. Okay. Now see the second part what it says. For second part, the kinetic energy is equal to minus half into potential energy. But this is already given in the question that here kinetic energy is half of and with minus sign potential energy. So just substitute the value of your potential energy and take the half of it with negative sign. You will get the kinetic energy value. Okay. So we will get it equal to what? 13.58 electron volt. Okay. Now total energy of a system is what? Kinetic energy per potential energy. Because only your this energy will be calculated here. Total energy will be here equal to mechanical energy. Okay. That is equal to kinetic energy plus potential energy. That is equal to 13.58 minus 27.16. That will give you minus 13.58 electron volt. Thus the minimum work done required in to free the electron is 13.5 electron volt. Because this is like negative value of total energy. So if you have to remove the free electron to move it as a free electron, you have to do this amount of work in the negative term. So 13.58 electron volt will be the answer for this. I have taken negative of this. Okay, that is why 13.58 electron volt will come. Now third part is potential energy at separation of 1.06 angstrom is given here. So we have to, not given, but we have to calculate here the like a potential energy at the separation of 1.06 angstrom. So just apply the formula for that. You will get like K Q E Q P upon 1.06 into 10 to the power minus 10. After like solving it, what you will get? The value is equal to minus 21.73 into 10 to the power minus 19 joule. So this value you are getting here, like potential energy, and just divided by 1.6 into 10 to the power minus 19, you will get it in electron volt. Okay, that is equal to minus 13.58 electron volt here. So that was the calculation for this part, and the potential energy of the system at 1.6006 angstrom is like we have just found out, and it is equal to 13.58 with minus sign. Now we have to calculate here what uh, potential energy at a distance minus potential energy at distance 0.53 angstrom, because potential energy of the system will become here what? Here we have taken difference as 1.06 angstrom distance. So your potential energy of system will become what? Potential energy at 1.06 angstrom distance minus potential energy at 0.53 angstrom. Okay. Here in the first part we have taken here infinity, because infinity is taken as the reference point like default. But here 1.06 angstrom is given as your reference point. So we have taken here this value at the first place, and then potential energy at 0.53 angstrom will be taken at the second place. So after calculating these both the quantities or both the like energies, you will get what? This we have already calculated, that is minus 13.58 minus of potential energy is what? Minus 27.16, which we have already calculated. So just substitute the value. You will get 13.58 electron volt. Okay, so this is your total potential energy of the system. Thus, on shifting the zero at potential energy, work required to free electrons remain the same, and it is equal to 13.58 electron volt. So just you shift the zero potential energy, like here we have shifted it to 1.06 angstrom, but the like work required to free electrons remains same here also, because it is not dependent on your position, it is the difference only. So that is why it will give the same value. Okay, so just move to the next topic and clear these points. Now the third like second topic is of this is we have to study potential energy of a system of 3-point charges. Till now we have seen the potential energy of system of 2-point charges. Now we will see the electrostatic potential energy of a system of 3-point charges here. So let us now consider a system of 3-point charges Q1, Q2, and Q3 having potential position vectors R1, R2, and R3 respectively and from origin. Okay. So here you have 3-point charges like Q1 is there, Q2, and Q3. Okay, 3-point charges are there, and their respective distance from origin are what? R1, R2, and R3. So this will be like from origin. Let's take it like origin. So here this distance will be what? R1. This will be what? This will be R2. This is a position vector. So R2. This is R1. And this is what? R3. Okay. So it is not given, but you have to see that this is R1, this is R2, this is R3. So to bring Q1 first from infinity to position R1, so if you like bring the Q1 charge from infinity to position R1, no work is required, because we bring charge Q1 from infinity to a particular location where potential is 0, because there were no charges initially present in this space. So if you bring like Q1 here initially, like I will here draw the diagram. It is your origin, and initially there were no charges. If you bring Q1 from infinity to here, then it will come like this at R1 position, and it has no any potential energy in the system, like, but there is no potential difference from here to here, so that is why there is no electrostatic potential energy of the system here. Okay, so here that will be equal to 0. So work is required also 0. So therefore work done, work 1 equal to 0. It is written also here. The work done in bringing Q2 from intermediate to position R2 is given by. So if you now bring Q2 at R2, like if I bring Q2 here at R2 position, okay, this is R2. So now you have to do some work because Q1 charge was already present here. So you have to do the work against the field of this charge. So what will be the work 2 is equal to, that will be equal to Q2 into V1. Yeah, it means that what the charge we have to bring into the potential which was present initially there. So V1 was the potential presented initial there. So that is the formula we will apply here. So it will like give you what? And it will give you K Q1 Q2 upon R12. Okay, R12 is what? This is distance between Q1 and Q2. So if you take the difference of these distances, R2 minus R1 will come, and you can write it like what? R12 or R21, or you can write it R1 minus R2 also. So it will come as R12 position vector of this distance between this. So now this was the work done by so bring the charge 2. This was work done 2, that is W2. Now we will see that what is the work done 3 to bring the third charge at the like position R3, position vector R3. Okay, so I will rub this. So now we will move a Q3 charge here. So the work done now will be equal to what? It will be equal to, okay. So after bringing the charges Q1 and Q2, it produces a potential which is at point P, and given by the formula what? 1 by 4 pi epsilon naught Q1 by R13 plus Q2 by R23. So this is now the electric potential because two charges are present now here in the space where we have just seen the observation of our calculation. So these are two charges, and the potential due to these charges will be equal to the sum of each potential. Okay, so that is the value of this. What done is bringing Q3 for infinity to position R3 is Q3 times V12 at R3. Okay, now if you bring like uh, Q3 charge here, so work 3 will be equal to what? Q3 into V12. Okay, and V12 value is what here? You just substitute the value of V12, you will get K Q1 Q3 upon R13 plus Q2 Q3 upon R23. So this is your total work done to bring the charge like Q3 at the respective position. So that is the expression for what? Your work done to bring the charge like third one. Okay. Now we will see that what is the total potential energy of the system after bringing the charges here. The total work done in assembling the charges at the given location equal to the potential energy of the system. So it is the like potential energy of the system, and it is obtained by adding the work done in different steps. So I will add the work done in different steps. Work done in bringing charge 1 was 0. Then 2 was 1 by 4 pi epsilon naught Q1 Q2 by R12, and third was 1 by 4 pi epsilon naught Q1 Q3 upon R13 plus Q2 Q3 upon R23. So just add the total work. You will get the expression as 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Just see here, it is also written here. So you can like observe it. This result can also be expressed in summation form. So this can also be written in summation form by using the summation formula. So just see here. Yeah. If you like write Q, that is the total potential energy of the system U is equal to what? A times, and it is sigma, or in like summation of I1 to 3 and J1 to 3 only. I is not equal to J here. Okay. And Q, it is equal to Qi Qj upon Rij. Okay. Rij. So if you expand it, you will get like what? K into Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Okay. Because I is not equal to J here. So each time you will get Qi Qj as different terms like Q1 Q2 Q2 Q3 like this. Okay. So that was the summation formula for this. Now we will move forward and see what is the next topic. Okay. Okay. So here it is written that due to conservative nature of electrostatic force, the value of capital U is independent of the manner in which the configuration is assembled. Okay. So you can see that electrostatic force has the conservative nature. So the value of U is independent of the manner in which the configuration is assembled. Okay. Because it is your conservative force. So work done in bringing any charge from one point to another is not dependent on the path. It will depend on the final and initial position. That is why you are getting the result like this only. That it will depend on your configuration also. Okay. Means it will independent on the configuration. Like if Q2 is there and Q3 is there, so Q4 is there. So it will not depend on the configuration. Here it is written there. The value of U is independent of the manner in which the configuration is assembled. Okay. Like if you bring the Q3 charge from here to here, by which path, any path, it will does not depend on the configuration by which it is formed here. So that is written here. If we write the resistance Ri minus Rj mod as Rij, the above equation may be expressed as for the system of n-point charge. So it will be written like 1 by 4 pi epsilon naught Ij 1 to n and J1 to n Qi Qj upon Ri. So that is similar to what I have told you in the summation formula. So that is just similar to that. So you don't have to see this point. Okay. Electrostatic potential energy of a system of n-point charges is equal to the total amount of work done in assembling all the charges at the given position from infinity. Okay. So that is also very obvious that we have already calculated it, that if we bring the charges from infinity to a specific point, then the net or total potential energy of system is for n-point charges equal to the total amount of work done in assembling all the charges at the given position. Okay. So all the points in this page, I think that you are clear for that. The SI unit of electrostatic potential energy is Joule, because it is a analogy to work done only, and it is just a work done in bringing a charges to a specific point. So its SI unit is what? Joule. Another convenient unit of energy is electron volt. Sometimes we use electron volt also as a unit of energy, and it is widely used for charged particles. So 1 electron volt is equal to what? 1.6 into 10 power minus 19 coulomb into 1 volt. Okay. Because electron volt is written like what? Electronic charge into 1 volt. So that is why 1.6 into 10 power minus 19 coulomb is multiplied by 1 by 1 volt, and it is coming out equal to 1.6 into 10 power minus 19 joule. Okay. Because coulomb and volt multiplied give you joule. Now see the example 15 here. Yes, yes. Three charges, all Q equal to 10 coulomb, are placed at the edge of an equilateral triangle of side 2 meter. Find the net potential energy of the system. So there are three charges which are placed at the edge of an equilateral triangle of side 2 meter, and we have to find the net potential energy of the system. How to do this? So there we have just calculated the total potential energy of 3-point charges. We will use the formula of that only, and just to see that if each charge of 10 coulomb is placed at like side of equilateral triangle r is equal to 2 meter. Okay, they are placed at vertices. No, at the edge of. Okay, at the edge of that equilateral triangle. So potential energy between two charges is given by what? K Q1 Q2 by R. R is distance between Q1 and Q2. Potential energy of system will be 3 times the potential energy between the two charges because these are symmetrically placed here, and the configuration is symmetric here. So system will be 3 times the potential energy between the two charges as the equal charge is placed at the vertices, okay, of equilateral triangle. So these are like placed at the vertices of equilateral triangle and all are of equal magnitude. So we will just apply the formula 3 times KQQ upon R. Okay, because the charge values are also equal. So we will just apply this formula and we will get what? Potential energy net will be equal to 3 times 9 into 10 to the power 9 into 10 into 10, that is the magnitude of the charges, upon distance is what? 2, because side length is what? 2. So just calculate these values, you will get 135 into 10 to the power 10 joule. Okay, just do the calculation part, you will get the answer. Now we will move further and see what is the next thing. So I should rub this. Yes. 3-point charges Q, 2Q, and 8Q are to be placed on a 9 centimeter long straight line. So there are 3-point charges whose magnitude are Q, 2Q, and 8Q. They are to be placed on a 9 centimeter long straight line, and they have to be placed on a long 9 centimeter straight line. Find the positions where the charges should be placed such that the potential energy of the system is minimum. In this situation, what is the electric field at the position of the charge Q due to the other two charges? So we have to find the configuration or like their uh, such a position of three charges where the potential energy of system is minimum. Okay, so where is the potential energy minimum? Potential energy is minimum when we use the formula of what? Your minimum maximum concept can be used here. Okay, so just write the formula of your U here. That is the potential energy of the system. So if you write the potential energy of the system, so you can observe here that 3-point charges are placed like this only. Okay, I have just taken a Q charge in the between, and distance of 2Q charge is x distance from it. So this charge 8Q will be equal to what? 9 minus x, because whole distance is 9, so this will be equal to 9 minus x only. Okay. Now just apply the formula of total energy or potential energy of the system here. You will get what equations. So it will be coming out equal to K times 2Q into Q. 2Q into Q upon x, because distance between them is x only. Okay. For the second pair, that is 8Q and Q, you will get 9 minus x as the distance. See here, 9 minus x. And for 2Q and 8Q, for these pairs, you will get the distance as 9 only, because the distance between them is 9 centimeter. Okay. So after doing the calculation here K, okay, for U to be minimum, 2 by x plus 8 by 9 minus x should be minimum. Okay. Why is it so? Because this is your constant term. Okay. So you will get your variables from this only, these two terms. So just apply the differentiation of this whole term, d by dx, take the d by dx of 2 by x plus 8 by 9 minus x. These q and q will be common and cancel out. So we will not consider this. We will only take the variable terms and the multiplied constant with it. So 2 by x plus 8 by 9 minus x is like differentiated, and it is it's placed with 0. After doing the differentiation of this, 2 by x differentiation is what? Minus 2 by x square plus 8 upon 9 minus x square is the differentiation of second part with minus of 1 also. See here. Like if you do the differentiation of d by dx of 8 upon 9 minus x, what is the result? D by dx of this is 8 by 9 minus x square. And what minus x differentiation is what? Equal to This is like differentiation of first part, minus 8 by 9 minus x whole square. And differentiation of minus x is minus 1. That is why you are getting the result as 8 upon 9 minus x whole square. See here, that is written here also. So it will be equal to 0. And if you now do it further calculated, further calculation, you will get x by 9 minus x equal to 1 by 2. See here, if you do here minus 2 by x square or 2 by x square equal to 8 by 9 minus x square. You can write like that only if you like move it in this side. So now just take x here right hand side. So x upon 9 minus x will be equal to what? 1 by 4 to the power half. That is equal to 1 by 2 only. So x is equal to what? X upon 9 minus x is equal to 1 by 2. So 2x is equal to 9 minus x, or 3x is equal to 9. X is equal to 3 centimeter is the answer. So that is why they have used these formulas, and that is distance of charge q from 2q should be 3 centimeter. Okay, so for minimum potential energy, your distance of charges q from 2q should be 3 centimeter. Electric field at q will be what? E is equal to k into 2q upon 3 into 10 power minus 2 whole square minus 3 k into 8q upon 6 into 10 power minus 2 whole square. That is equal to what? 0. It is coming out to be equal to 0 here. Okay. So electric field at E, like at Q, this point, at this point. So that will be equal to what? It will be like due to 2Q charge and 8Q charge. And you know that if your system is like at minimum potential energy, so electric field at this point should be 0. So here it is coming out to be equal to 0. Okay. So that was the calculation of this part. Now we will move further and see what is the next thing. So there is a example 17 also in this chapter. See what is it saying. If one of the two electrons of hydrogen molecule is removed, we get a hydrogen molecule ion H2 plus. So this is like obvious thing, because if you remove two electrons from hydrogen molecule, then the molecule ion will be H2 plus. In the ground state of an H2 plus, the two protons are separated by roughly 1.5 angstrom. Okay. So in the ground state of an like H2 plus, the two protons are separated by roughly 1.5 angstrom, and the electron is roughly 1 angstrom from each proton. So this is the distance between like electron and proton. Determine the potential energy of the system. Specify your choice of the zero of potential energy. Okay. So there are protons P1 and P2 with an electron E. So assume that here configuration. So there are two protons here, P1 and P2, which are separated by 1.5 angstrom distance. That is like told here also. And your electron and proton first, and electron and proton second are also separated by distance 1 angstrom both each of them. Okay. So both are equal, like 1 angstrom distance between each electron and proton. So distance between two protons is given by R1, that is equal to 1.5 angstrom. So you can also see here that this distance is what? This is your R1 only. Okay. So it is 1.5 angstrom or 1.5 into 10 power minus 10 meter. Distance between proton P1 and electron E is given by, just a second. Yes. So it is given by R2 and it is equal to 1 angstrom. See here it is a 1 angstrom. It is specified also here. So it is equal to 1 into 10 power minus 10 meter. The total potential energy of the system is what? This is the sum of the each potential, okay, potential energy of the each charge system. So you will get equal to k times qp1 qp2 upon r1 plus qp1 qe upon r2 and qp2 qe upon r3, because all the charges will like contribute here. Each configuration will contribute here what? Potential energy. So we will get this expression. Now, given values are like QP1, QP2 are 1.6 into 10 power minus 19 coulomb. This is the electron, like protonic charge value. Okay. Just now, what you do, substitute the values here. You will get the result only. So U is coming out to be equal to what? 19.2 electron volt. Here he has done the calculation like what? 9 to 10.9, 1.6 into 10 power minus 19. That is the value of protonic charge into 1.6 into 10 power minus 19. Two protons are there. So two times charge values are multiplied upon 1.5 into 10 power minus 10 meter. Okay. Similarly, for your electron proton pair, this is the value, and similar is for second electron proton pair. After adding these all terms, you will get the result of minus 19.2 electron volt. Because it was coming in joule, you have to divide it by 1.6 into 10 power minus 19 to get it in electron volt values. Okay. So here we use the potential energy at infinity 0. So that is the obvious thing that we always assume that potential energy at infinity is 0 if it is not mentioned specifically. Okay. Now I should delete this part and potential energy in an external field. Now we have the like next thing, that is potential energy in an external field. Okay. So we have already seen like this topic. We have seen that what is the potential energy of dipole in an electric field. So we will now see it again. So a single charge or a system of charges possess electrostatic potential energy in the presence of an external electric field. These are discussed as follows. So if a system of charges like dipole is placed in an uh, external electric field, so it possesses like what electrostatic potential energy also. Okay. So we will see that how to calculate this potential energy. So the potential if electric field is applied here, so it will apply on dipole so that it rotates from angle theta 1 to theta 2. Okay, with respect to the electric field here. Like if you have electric field here and this field direction is like this only. Uniform electric field lines are there. And if your dipole is placed inside this electric field, minus q and plus q are there. So the electric field is making angle theta with the dipole direction. Okay, dipole moment is like from minus charge to plus charge. Your p will be in directed in this direction. Okay, so it is making theta angle with the electric field. The amount of work done by the external torque is given by this. We have already seen in the previous chapter. So work done is what? It will like moving the your system from one theta 1 to another theta 2, and there some torque external will be applied here with the theta d theta. So this is the expression for the work done in rotational mechanics. So theta 1 to theta 2 torque external theta d theta is a work done, and it is coming out to be equal to what? Because here your tau your torque value will be coming out equal to what? Pe sine theta. Okay, this is your work done in value. Okay, not torque, because if you calculate the torque into theta here, you will get Pe sine theta only. Okay. So just integrate it from theta 1 to theta 2, you will get sine theta integration is minus cos theta, and after substituting the limits, you will get the result at Pe cos theta 1 minus cos theta 2. So this is very important result, like amount of work done by external torque. So you have to remember this. The work done W is stored as the potential energy of the system. So this work done is like stored as the potential energy of the system, because it is stored inside them. Therefore, the potential energy of the dipole placed in the external field is given by what? Pe cos theta 1 minus cos theta 2. Okay. So I hope you got this point also. So let's move further and see what is the next thing. Potential energy in an external field. So this we have just calculated that what is the potential energy in an external field of a dipole we have just seen. So we will continue with this further. So potential energy of a single charge in electric field. If a single charge is placed in an electric field, external electric field, so if we it has a position vector r in an external field, so the work done is equal to what? Q dot V. Okay, where VR is the potential at the point due to external electric field E. So here it is what? Suppose here you have like point charge placed in an electric field, uniform electric field. So it has like position vector r from the origin, and here some what potential will be of the function of r. So that is how this formula is written here. That work done is equal to Q dot V function of r, where VR is the potential at the point due to the external field E. Okay. So here what is VR? It is the potential at this point due to the external field capital E. Now potential energy of system of two charges in an external field. Okay. So we have to see the next thing that is equal to, that is the next topic. Okay. Next thing we will see here. So just the potential energy of system of two charges in an external field. We have to see this topic. Okay. Just a second. I will remove this part. For a system of two charges, Q1 and Q2, the potential energy is given as. So the potential energy of two system of charges is given as Q1 dot V R1. So that was like potential energy due to two point charges. Okay. So for a system of two charges, Q1, Q2, the potential energy is given as Q1 dot V plus Q2 dot V, and V the function of R1 in the first case, that is Q1 dot V R1. Okay. Q1 dot VR1 plus Q2 dot VR2 plus Q1 Q2 by 4 pi epsilon naught into R12. Okay, where Q1 Q2 is R2 point charges at position vectors R1 and R2 respectively. So here Q1 and Q2 are what? 2 point charges at position vectors R1 and R2, and VR1 is potential at R1 due to the external field, and VR2 is the potential at R2 due to the external field. Okay, so this, I hope you got this point also. That this is the formula for what? Two charges in an external field. So this extra term is coming out here. This is due to the configuration of two charges in the external field, and this is like position of these charges in the external field. Okay. So the summation of this will give what? Potential energy of system of 2 point charges in an external field. Okay. So let's move further and see what is the next thing. Potential energy of a dipole in an external field. So this we are already covered right now. So we will skip this because it is just equal to what? PE cos theta 1 minus cos theta 2. The work done W is stored as the potential energy of the system, and it is stored as the potential energy of the system. Therefore, the potential energy of the dipole is an electric field is given by P is cos theta 1 minus cos theta 2. Okay. So I hope that you got these all things. And yeah. So we will see one example like on this topic, and we will continue our like discussion for the next class, because we have covered many things today. Okay. So yeah, we will see this example. So here what is given in the question: an electric dipole of length 4 centimeter when placed with its axis making an angle of 60 degree with a uniform electric field. Okay. Experience a torque of 4 root 3 Newton meter. Calculate the potential energy of the dipole if it has charge plus minus 8 nanocoulomb. Okay. So this is given in nanocoulomb. Now you have given length 2a here. What is that? That is equal to 4 centimeter, because we already have seen that the distance between two dipoles is two charges of dipole is taken as 2a or 2l. So we have considered that length only. Now we have to like see the angle here. Angle is theta, which is equal to 60 degree here, and yes. and charge value is 8 into 10 power minus 9 coulomb. We know that torque is equal to what? Q into 2A into E sin theta. Okay, because your torque is only what? It is equal to torque is equal to what? Tau is equal to PE sin theta. Okay, so just apply that formula. Electric field will be coming out equal to what? Tau upon Q into 2A sin theta. Okay, because we have just cross multiplied it. Okay, and P value is Q into 2A. P is Q into 2A. Q into 2A. Okay, so potential energy of system will be equal to what? Minus P cos theta equal to minus Q times 2A into E cos theta. Okay, now just apply the formula and get the result. You will get it equal to minus 4 joule. After calculating this part, you will get the result as minus 4 joule. Okay, so this is your final answer for this system. Just substitute the values, you will get this answer. So I hope that you liked the today's session. So I will now end this lecture here, and we will continue the rest part in the next lecture. And till now, I hope that you like the lecture. And if you have any suggestion or doubt, you can ask in the chat box. If you also want to ask for one-one session, one-to-one session, or private session, you can also tell us. Okay. So thank you for today's lecture. Have a great day.